Hi everybody, I hope this video finds you well. In this video, we're going to be finishing up our section on probability by talking about a very sort of important special type of probability situation called a binomial probability experiment. And we will see that a binomial probability experiment is sort of the follow-up to using the counting that we learned a couple videos ago in regards to an independent probability situation. So to do that, we're going to give a definition, talk about a very important formula, and then look at a couple examples here. So we need to define what a binomial probability experiment is. So a binomial probability experiment is a probability experiment that follows three major rules. First, as the name would imply, we've actually heard that term binomial before, right? We sort of talked about a binomial categorical variable as a categorical variable that only has two categories. Well, a binomial probability experiment is similar. So the first rule for a binomial probability experiment is that for each trial of the experiment, there are only two outcomes. So in other words, whenever you do whatever this probability experiment is, there are only two possible outcomes. We are going to call these outcomes or reference these as a success and a failure. Now, there are certain things out there that are very naturally binomial. You flip a coin and you look for heads. That is naturally binomial. You get heads, that's a success. You get tails, that's a failure. There are things out there that are also sort of naturally binomial. You ask people a question like, do you agree with this statement? They say yes, that's a success. They say no, that's a failure. Now, there are other things out there that maybe are not naturally binomial, but we can make them binomial. You might ask somebody, what is your political affiliation? And they might give you answers like Democrat, Republican, Independent, Green Party. They could give you lots and lots of different answers. So there wouldn't be only two outcomes. But if you ask that person, are you a Democrat? And they answered yes or no, then you could think about it as a success and failure. If you ask them, are you a Republican? Then you could think about it as yes as a success, no as a failure. So the idea is that sometimes things are naturally binomial, but we can also make things binomial by making sure that we are only interested in two possibilities, a success and a failure. The second big rule of a probability experiment is that each trial, every time we redo the experiment, it has to be independent. So you can see how this is going to be a parallel to what we did in the last video, where we talked about how to sort of handle complex dependent situations. Now everything is going to be independent. Finally, the sort of third and final requirement is that we have to know the number of trials, which we call n. In other words, how many times are you going to run the experiment? And the probability of success on a single trial, which we call p. So you have to know n and p. Technically, n and p are what we call the parameters of that binomial probability experiment. Now, it's not necessary, but you should just make a note here. Since there are only two outcomes, since there is only a success and a failure, and this is the probability of success, you also know that the probability of failure is 1 minus p. How do we know that the probability of failure is 1 minus p? Well, there's only two outcomes. If the probability of success is p, then everything that remains, 1 minus p, has to be the probability of failure. So you don't need this stated, but keep in mind you can always get this by knowing the probability of success. Okay, so how do we work with these binomials? Well, luckily, there's a very sort of famous and important formula that helps us calculate the probability when we're in a binomial probability experiment. So this is what's called the binomial formula. So this says if you have a binomial probability experiment, so you have something that follows all three of these rules, you have n trials and probability of success p, then you can calculate the chance that you get exactly k successes, so you get k successes with n attempts by this formula here. And this formula says you do nck, so you do the number of combinations when you choose k from n, you do p to the k, and you do 1 minus p to the n minus k. Now, this formula, it's a very famous one in mathematics. It's a little beyond the scope of our class to prove where this comes from, so I just want to diagram out some important parts of this. First of all, this p right here, well, we know that that is the probability of success. And since we just talked about it, that 1 minus p right there, that's the probability of failure. What exponent do we use here? Well, we use k, which is the number of successes. So that is the number of successes. Now you might ask yourself, okay, what's this n minus k? Well, if you've got n trials, so you're going to do it n times, and you're going to have k successes, then whatever remains, n minus k, must be the number of failures. So this exponent up here, this is the number of failures. So in other words, what you're doing is you're taking the probability of success and raising it to the number of successes, and the probability of failure and raising it to the number of failures. What does this thing out here then do, that NCK? Well, this counts all the different ways to get K successes in N trials. So this counts all the different orders. And if you think back way back to when we first started talking about this multiplication and these multiple events, we did an example where we were doing like a basketball player shooting free throws, and we were making little diagrams where we had to go like check, check, X, and check, and X, check, and all that stuff. Well, this NCK actually counts that for us. So this really ties it into why we took the time to learn that counting stuff. So this formula here, this binomial formula, very, very important. It allows us to handle things in a binomial probability experiment. So let's take a look at using it in a couple different examples here. So let's take a look at this example here. For this example, we're going to suppose that the chance that a randomly selected adult in the US has a college degree is 34%. So in other words, 34% of US adults have college degrees. We're going to further suppose each adult is independent of one another, which should make sense. Knowing that one person has a college degree doesn't impact if you pick another random person that they would or would not have a college degree. And we're going to finally suppose you select a group of 11 US adults. So the first thing we want to do is calculate the probability that exactly 4 of the adults have college degrees. So let's think about whether or not this is binomial. So we'll make a little thing over here. Is this a binomial? Well, are there 2 outcomes? Well, when you pick one of these people, when you pick a random adult, there are only 2 outcomes. They either college degree, they have it, that would be what we call a success, or no degree. And that would be, in this case, what we count as a failure. So there are 2 outcomes. Is each trial independent? Well, they tell us right in here, yes, it is independent. And that should sort of tell you as a keyword, looking for that word independent, very important. So, independent. Check. Last thing, do we know the number of trials and the number of success? And the probability of success? Well, yes. The probability of success is right there. It's 34%. And the number of trials, well, we're going to take a group of 11 adults. So we know N is 11, and we know P is 0.34. Check. So all the things are sort of met here, right? We know that there are only 2 outcomes. You either have a degree or you don't. We know that each trial is independent, and we know the number of successes and the probability of success. It might not also be a bad idea just to jot down 1 minus P, the probability of failure. If 34% of people have degrees, then that means 0.66 or 66% of people do not. All right, so let's actually try to calculate the probability that exactly 4 have college degrees. So we're going to use that binomial formula. Remember, the binomial formula says the probability that exactly K successes is going to be NCK, P to the K, 1 minus P to the N minus K. So in our case, probability of exactly 4 have degrees. The N here, we said, is going to be 11. So we're going to do 11C. How many successes do we want? Well, we want 4 of them to have degrees, so 11C4. Probability of success, that's going to be 0.34. So we're going to do 0.34 to the number of successes, which we said we want 4 of them to have degrees, so to the 4th power. Then the probability of failure, which is at 0.66. And then to the number of failures. Well, if we want 4 of them to have degrees, and we have 11 people, that means that 7 of them, all those remaining people, must not have degrees. And if you think about it, that 4 plus 7 gives us the 11 overall. All right, let's go ahead and actually type that in and see what we get. So if we type that into our calculator, you can do this all in one line. So 11C4, and then just times, and use parentheses, 0.34 to the fourth, and then times 0.66 to the 7. You should get that that comes out as approximately 0.241. So there's about a 24% chance that exactly 4 of the 11 people will actually have a college degree. All right, so let's go ahead and take a look at the next one. All right, so let's go ahead and look at the next one that says we want exactly 5 of the adults to not have college degrees. Now, not having a college degree in our sort of setup here is actually a failure, not a success. So let's go ahead and rephrase this first in terms of the successes. This is the same as, well, if 5 of them are going to not have college degrees and we have 11 people, that must mean it's the same as having 6 have college degrees. So we're phrasing it, instead of in terms of the failures, in terms of the successes. So instead of thinking about it as 5 of them not having college degrees, we're going to think about it as 6 of them have college degrees. Now we can go ahead and use our formula again. So we still have 11 people. We're going to choose 6 of them to be the ones that have college degrees. The probability of having a college degree is 0.34, and we're going to raise that to the 6 because we want 6 of them to have college degrees. The probability that they do not have a college degree is 0.66. And since 6 are going to have college degrees and we have 11, that means we want 5 to not have college degrees. And we'll go ahead and multiply that out. So 11 and then C6, and then times parentheses 0.34 raised to the 6 times parentheses 0.66 raised to the 5th. And that should come out as 0.089. So there's about an 8.9 or almost 9% chance that exactly 5 of the adults will not have a college degree, which is the same as saying there's about a 9% chance that exactly 6 of them will have college degrees. All right, so these first two were pretty easy because they were only talking about an exact amount. And if you'll pardon the pun, that's exactly what the binomial formula is good at. Now let's look at some slightly more challenging ones. So the next one says we want less than 3 of them to have college degrees. So what does less than 3 mean? Well, that would be the same as exactly 0, 1, or 2 have college degrees. Right? If 0 of them have college degrees, that would be less than 3. If 1 has a college degree, then that's less than 3. And if 2 of them have college degrees, that's less than 3. So there's 3 different things we have to consider. So that means we're going to need to use our formula 3 times, 1 for each of these. So let's go ahead and do that. For 0, the number of successes is going to be 0. So we've got 11C0. We've got 11 people. 0 of them are supposed to have a college degree. 0.33 to the 0. And then 0.34, excuse me. So 0.34 to the 0, 0.66 to the 11. This right here would be all of them not having a college degree or 0 of them having a college degree. Then we're going to add. How do we know to add? Because we've got that or, because it could be this or this or this. Then we've got to do 1 person having a college degree. So 11C1 and then 0.34 to the 1, 0.66 to the 10. So this is 1 of them having a degree and 10 of them not. And then finally plus 11C2, 0.34 to the 2, 0.66 to the 9. This is 2 of them having the degree and 9 of them not. We'll do each of these individually and then add them up. The first one, 11C0, you'll see that that's actually 1 because there's only one way for none of them to have a degree, which is that they all don't have a degree. 0.34 to the 0 is also 1, so this just boils down, these parts don't matter, to just 0.66 to the 11, which should make sense. So if we do that, we should get that this is approximately about 0.010 plus, and then 11C1 times 0.34 times 0.66 to the 10. That should come out as about 0.059. and then plus 11C2 times 0.34 squared times 0.66 to the 9th. That guy should come out as 0.151. Then you just need to make sure you go ahead and add all those together. And when you do that, that should equal 0.010 plus 0.059 plus 0.151. That should come out as about 0.22. So there's about a 22% chance that less than 3 of them have college degrees. And that could be 0, 1, or 2 of them having college degrees. All right, one last one with this example. Let's try to do the chance that at least one of them has a college degree. So same idea, at least one could mean a lot of things. That could mean exactly 1, 2, 3, 4, 5, all the way down to all 11 have college degrees. Okay, now that doesn't look very pleasant to do because that means we'd have to use our formula 1, 2, 3, 4, 5, all the way down 11. We'd have to use our formula 11 times. So we could do that if you have a lot of extra time on your hands. Sure, why not? But we can do it a little bit better of a way. We can use the complement. Remember, the complement is 1 minus the probability of whatever is not on this list. Well, there's only one thing that's not on this list, right? You can have exactly 1, 2, 3, 4, 5, down to 11 people have degrees. The only option that's not listed here is exactly 0. So this would be 1 minus the probability of exactly 0, which would be 1 minus 11C0, 0.34 to the 0, 0.66 to the 11. That's none of them having a college degree. We actually already calculated this right here. So this would be 1 minus 0.010, which would be 0.99. So what this basically says is there's about a 99% chance that at least one of them has a college degree, which makes sense because it's a group of 11 people. There should be at least one, since about a third of the people out there have college degrees, at least one of those people out of the 11 should have one. It's about a 99% chance there. Okay, so that gives you guys a little bit of practice using this binomial formula. Let's immediately jump into another example of this just to get more used to using this formula. All right, so for this one, we're going to suppose that the chance that a Toyota Tacoma, which is just a brand of sort of Toyota truck, right, lasts for more than 200,000 miles is 3%. So the chance that one of these trucks goes for longer than 2,000 miles is 3%. We're going to also suppose that each Toyota Tacoma is independent of one another, which makes sense. If one breaks down, then another one doesn't care, right? They're independent of one another. And we're going to suppose that you randomly select a group of 20 Toyota Tacomas. And we've got these probabilities to calculate. So let's ask ourselves here, is this binomial? Are there 2 outcomes? Well, the 2 things we're interested in is, does it last for more than 200,000 miles? So we would count a success as lasts more than 200,000. The failure doesn't last more than 200,000. So there we go. So it has only 2 outcomes. The truck either goes past 200,000 miles or it doesn't. Are the things independent of each other? Well, it's stated right in there, independent. Actually, again, if you were doing this on like a test or something, right, you'd want to see that word independent there, and that's your sort of tip-off that you should even think about this binomial here. Finally, do we know the number of trials and the number of successes? Yep. The number of trials right there, we've got 20 trucks, and we know that the chance that they do last for more than 200,000 miles, in other words, the chance that they are successful, well, that's going to be n equals 20, and p is going to be 0.03. Remember, it would be 0.03 to represent that 3%. We can also make a note of the probability of failure, 1 minus p, would be 0.97 here, right? 97% chance that they do not last more than 200,000 miles. All right, so let's try to calculate the probability. Exactly 2 of them last for more than 200,000 miles. We can do this using our formula directly, so probability exactly 2. We've got 20 to pick from. We want 2 to last more than 200,000 miles. The probability that they last more than 200,000 miles is 0.03. We raise that to the number of successes. Then take the probability of failure, which is 0.97, and raise that to the number of failures. How many failures? Well, 2 successes, 20 trucks overall. That means we have to have 18 fail. Let's go ahead and multiply that out. 20C2 times 0.03 squared times 0.97 to the 18. And you should see that that comes out as about 0.099. So there's about a 10% chance, just a little under 10% chance, that 2 out of the 20 trucks would last more than 200,000 miles. All right, let's go ahead and calculate the probability that none of the Toyota Tacomas last for more than 200,000 miles. So for us, that would be exactly 0, which would just be 20C0, 0.03 to the 0, 0.97 to the 20. Now, since we have a little bit more space here, just keep in mind, anytime you do 20C0, that's just going to be 1. Anything to the 0th power is just going to be 1. So this is literally just going to be 0.97 to the 20th, which makes sense because basically what we're saying here is that you're going to have 0.97 have to happen 20 times in a row. So you're just doing 0.97 times 0.97 times 0.97 20 times. If you do that, and you actually type that in, you should get that that comes out as approximately 0.544. So this is saying there's about a 54% chance that if you have a group of 20 Toyota Tacomas, none of them last for more than 200,000 miles. So that's more than half the time. All right, last one. The probability that at least 2 of them last for more than 200,000 miles. So what's at least 2 here? At least 2 would be, well, it could be exactly 2. That would be at least 2, or 3, or 4, or down to 19, or all 20 of them. So if we do it this way, we'd have to do 1, 2, 3. It looks like we'd have to go all the way down to like 19 different computations to do that. We're going to try to use that complement rule again, right? There's too many things to add up there. So let's do this as 1 minus the probability of exactly, well, what's not on this list? Well, the things not on this list, since this goes from 2 up to 20, would be 0 and 1. So it would be 1 minus the probability of exactly 0 or 1. So we can calculate that. That's 1 minus. There's still 2 options here, so we're going to have to go ahead and use our formula twice. First one would be 20C0, 0.03 to the 0, 0.97 to the 20, plus, now we're going to do the exactly 1, so that would be 20C1, 0.03 to the 1, 0.97 to the 19. This would be then 1 minus, and notice these parentheses are going to make us add these 2 things first and then subtract it from 1. So this right here, we already did this guy, would be 0.544. And the other one would be 20 times 0.03 times 0.97 to the 19. That looks like it would come out as about 336. And if we do that, 1 minus parentheses 0.544 plus 0.336, that looks like it should come out as 0.12. So there's only about a 12% chance that at least 2 out of those 20 trucks will last for more than 200,000 miles. So these 2 examples basically show you guys how to use this binomial formula when you have a binomial probability experiment. Unfortunately, while this formula is nice and useful, as you guys can see, sometimes it gets very computationally intensive when there's lots of different possibilities, right? As we saw here, this was only a group of 20 trucks, and already we had to get sort of lucky that we could use this complement rule to take care of this. Fortunately, when the number of trials gets really large, so if we were talking not about 20 trucks, but we were talking about like 200 trucks or 500 or 1,000 trucks, there's actually an even faster way to do this, based on something we saw very early on in our class, the normal distribution. So our last topic we're going to talk about here is how to approximate the binomial with the normal distribution. So let's go ahead and talk about that. So this is what's called the normal approximation to the binomial distribution. Basically what this says is that when the number of trials is very large, so if you have a very large number of trials or a very large group, you can actually approximate this binomial with the normal distribution, which was something we talked very early on in our class with that table A and the z-score and all that stuff. The first question you might ask yourself is, what does large mean? I mean, does large mean 100? Does large mean 10,000? Well, it turns out that we have a statistical condition. The way we check if something is large is we confirm that n times p times 1 minus p has got to be greater than or equal to 10. So you have to check this to be able to use this approximation. If this isn't true, then you cannot use this approximation, and you're forced to use that formula that we were just using in the last two examples. All right, if this condition is satisfied, if n times p times 1 minus p is greater than or equal to 10, then you can use a normal approximation. And remember, when you approximate things with a normal, you need to know their mean and standard deviation. Well, the mean will be n times p, and the standard deviation will be the square root of n times p times 1 minus p. So let's go ahead and take a look at an example of using this normal approximation. So we've got this example here. We're going to suppose you are studying admissions into a large university. You find that 9% of the students that apply to this university are accepted. And we're going to further suppose that each student is independent. And finally, we're going to suppose that you are studying a group of 500 students who apply to this university. For this guy here, first thing we should do is just make sure that this thing actually is binomial. So let's just make a little note here. Why would he even take the time to think about the binomial? Well, it's because we see that word independent in there. So, are there two outcomes here? Well, they either are admitted, or I guess we could say accepted. They're accepted, not accepted. So when you apply to a school, they are either accepted or not accepted, so there are only two outcomes. We know that it's independent. Good. And do we know the number of trials and the probability of success? Yeah, right? We know that n is 500. We've got 500 students here. And we know the probability of success, the probability a student gets in, is 0.09. We could also make a note. We know the probability of failure, 1 minus 0.09, is going to be 0.91. So we've got all three things that make us know that this is a binomial. But we should be suspicious. 500 seems like a large number of trials. So notice that the first thing we're asked to do here is explain why it's appropriate to use the normal approximation in this situation. So how do we do that? Well, we check. We check that statistical condition. We do np 1 minus p. So let's multiply that out. N is 500, p is 0.09, and 1 minus p, we just said that's 0.91. So we multiply those things together, 500 times 0.09 times 0.91, and we get 40.95. Is that good? Is it bad? Well, it's good, right? That is greater than or equal to 10. So we are all good. So we can say it is appropriate to approximate with normal distribution. So this is the check that you need to do to make sure that you can actually approximate with the normal distribution. So let's calculate the mean and standard deviation then, since we know that it's appropriate to do this, and we need those things to make a normal distribution. So the mean will be n times p, which in this case is 500, times p, which is 0.09. Multiply that out, and we get 45. What would this actually be as the sort of units? This would be 45 students accepted. Now, this formula might seem weird to you, but this number should make sense. What you basically did here is you said, on average, if you look at 500 people who apply and 9% get in, well, what's 9% of 500? 9% of 500 is 45. So we're saying on average, 45 students should get in out of every 500. Then, of course, it's not always going to be 45 students. So there's going to be an amount of deviation. We use that standard deviation here. It'll be the square root of np1 minus p. Keep in mind, you've already calculated np1 minus p. It's right here. So you can just do this as the square root of 40.95, which is going to be a little bit messy, but we just use our calculator, square root 40.95. Looks like that should come out as about 6.4 students accepted. So on average, 45 students out of 500 should be accepted with a standard deviation of 6.4 students. So let's use this then to calculate a couple probabilities. First thing we want to calculate is the probability that less than 50 of these 500 students are accepted. So how would we do this? Well, we could say, okay, less than 50. That means 0, 1, 2, 3, 4, 5, all the way up to 49 and try to use our binomial formula. But that sounds really horrendous because that's going to be 50 calculations. So instead, we want to use this normal approximation. So we can do that. We can draw our bell-shaped curve. This should feel sort of familiar. We can put our middle here at our mean, which is 45. We're interested in 50, right? Less than 50. So 50 would be located over here. And then, of course, we'd be shading in the stuff to the left because we're interested in the probability that less than 50 are accepted. Then we could go ahead and calculate our z-score. Z would be x minus mu over sigma, which in this case, the x is that 50 minus the mean, which is 45, divided by the standard deviation, which is 6.4. If you do that, you should get that that's 5 divided by 6.4, which should be about 0.78. Then we go ahead and we look this up on table A. Let's go ahead and do that real quick. There's table A. We'll need the positive side. We're looking for 0.78. So if we do that, there's 0.7 and there's 0.08. So we're right there. So we should get 0.7823. So let's go back. So we find 0.7823. Let's put that onto our diagram. That's the stuff to the left, 0.7823. Does that match up to what we wanted? It does. So that is our probability. So we can say the probability less than 50 accepted is 0.7823. So if you've got 500 students that apply, the chance that less than 50 are accepted is about 78%. All right, let's try this again. Let's try to calculate the probability that more than 35 are accepted. So same idea, draw your bell-shaped curve. Put the middle at the mean. Now we're interested in 35. So we'll put 35 over here because it's smaller than the mean. And we want more than 35. So this time we'll be shading in to the right because we want more than 35 to get in here. Okay, we'll go ahead and calculate that z-score. Z is x minus mu over sigma. Z then, the observation in this case is that 35. So 35 minus 45 over 6.4. And looks like that numerator is going to be minus 10 divided by 6.4. And looks like you should get about negative 1.56. Notice, again, negative z-score makes sense because 35 is below the average. Okay, we go ahead and we look that up on table A. So let's go ahead and do that. We need to look up negative 1.56. So there's negative 1.5. There's the 0.06 right there. So we should get 0.0594. So let's put that in, 0.0594. We can fill that in for our table. That's the stuff this way, 0.0594. Does that match our shaded area? Well, this is the stuff to the left. We wanted the stuff to the right, so no. So our shaded area here would be 1 minus 0.0594, which would be 0.9406. So that's the probability we actually wanted. That's our shaded area. So the probability more than 35 accepted would be 0.9406. In other words, there's about a 94% chance that more than 35 of these students would be accepted. So this is a sort of very special application of the normal distribution when you have a large amount of trials. Keep in mind that for this class, you guys are not going to have to guess when to do this. If a question sort of wants you to do this, there's going to be a part that asks you to confirm that it's appropriate to use this approximation. So you guys only need to worry about doing all this if you see something that directly mentions the normal approximation. This actually finishes up pretty much everything we needed to talk about for probability. This is everything you guys need for exam 2. So in our next video, we'll be moving on past exam 2 into new material.